In our last video, we have derived the mechanical model of an electric machine. Now we are ready to derive the electrical dynamics. Before that, we need to first review on the circuit fundamental. So consider figure 2, this simple electrical circuit. We have voltage source, we have a simple model for a coil inductance, which consists of its resistance and inductance. We are assuming the voltage across the electric circuit, the inductance is E1 in this direction. By Kirchhoff's voltage law, we can write down the voltage equation. It's U1 equal to R1 times R1, I1 and plus the voltage across the inductance. This term is known as a counter-electromagnetic force, EMF. We are now going to use the energy method to derive an expression for our electromagnetic torque. So this is our mechanical dynamics. In this equation, we have two unknown variables. The first is the electromagnetic torque. The other is unknown external disturbance torque by another mechanical source. So we are now interested to derive the electromagnetic torque first. To do that, we are now going to assume we don't know the law of Lorentz force or Ampere's force. We are simply using the conservation of the energy to derive an expression for our torque. To see that, we need to first calculate the electrical power applied into the circuit, which is simply the time integral of the product of U1 and L1. It consists of the heat. So simply we plug in the equation for U1, which is R1 I1 plus E1. So the resulting energy are heat and magnetic energy. We are denoting them as W copper and W phi. And note that equation 25 is true only when the mechanical speed is 0. In general case, when for example, we have some kind of rotor with magnet that's spinning at a speed at omega, we need to further account for its mechanical power, mechanical energy into the equation of the energy balance. So we have electrical input and mechanical power input, and those input power will be converting into copper loss or Joule loss, magnetic energy and the kinetic energy of a rigid body that's rotating. We are now going to take time derivative to both sides to derive this equation, and note that the copper loss is eliminated by the other term. So that's inside here we have I squared R1, and also note that this term is equal to, also including this inertia, it's equal to TEM minus T load torque, and it's also gone. Finally, we are deriving this equation. We will later see that this is actually an expression for the total differential, or you can say it's an exact differential of the magnetic energy. So this is a magnetic energy. The time derivative, it equals to the torque times the angular speed times the current times E1. We know the magnetic energy or the magnetic field is a conservative field. So it is possible to eliminate the dependence of time from this equation. If we plug in the Faraday's law of induction, so E1 is can be replaced with d psi over dt. So this is the flux linkage of the circuit. Then we can eliminate dt from both sides of the equation. Then this equation is becoming independent on time. That's why we say we have derived the total differential for our magnetic energy. It depends on two independent states, The first one is angular location of the rotor. The other is the flux linkage of the coil. It is also possible in a balanced three-phase system. For example, we have three circuits denoted by 1, 2, and 3. It is possible the magnetic energy does not change. Or we can say it's time invariant. So this term is 0. Then we can directly calculate torque by plugging the electrical power that's absorbed by the back EMF of the three-phase back EMF. So this equation has been used in this reference by Professor Lee. Yep, you can check it on this reference. So another idea is that we can fix our rotor such that our rotor is not moving, so theta is constant. Then we can simply derive that dw phi over dt is equal to E1I1. So we can we can integrate for our magnetic energy by, that's it. So to note that we do have some constant energy that's present here. It is possible that's contributed by some permanent magnet because we haven't really modeled the permanent magnet yet. So apparently the permanent magnet here contribute to some kind of magnetic field, so it has energy in it. Later we are going to also model the permanent magnet as a circuit. So it's basically, this is a permanent magnet. It's equivalent to a circuit. We are going to name it as IM+1. Yep. So such that it generates magnetic field. So this constant term actually compensates for the magnetic energy that's provided by the permanent magnet field we haven't really considered here. Okay, so one thing to note that we have used a different expression for our Faraday's law of induction in the above. This is the original definition for that. This is valid for only one turn of coil, so it's N1 is 1. This equation relates the magnetic field with a circuit quantity E. So this is circuit, and this right hand side is really the magnetic field. It's a field quantity, and it's difficult to use because if we want to solve for the field quantity, we really need to actually solve for the PDE. That's basically the Maxwell's equation for that. For example, B is some kind of no, it's not a closed circuit. It's something like this, right? And B is I remember it's kind of like something like that. The magnetic potential can be solved by some finite element analysis tools. So that's too complicated. We really need some analytic model for our electrical machine. We will later use for control. So we are not going to do that. To avoid those field quantity, we introduce a different variable that's only valid in a circuit. So it's defined as the flux linkage. It's equal to the time integral over the back EMF over time. And the sign is not yet defined here. In this course, we are using motoring convention, which actually defines the equation to be like this. Okay, this is really a definition. It's not really related to any physical phenomenon. And flux linkage is related to the magnetic flux by this equation. One is the turn number for the coil. Okay, so in this equation, the flux linkage has been defined as the integral of over voltage, for actually in Newton's law, the momentum can also be calculated as a time integral. So it's something like this. So there's some kind of analogy between these two motions laws or motion equation. That is, the voltage is the force and flux linkage is the momentum, right? So we call this analogy the force voltage analogy, and in fact, current is analog to velocity, and the electrical charge that passes through a cross section, if we take the time differential, time derivative of it, it gives us the current I1. Now we are ready to further derive the equivalent inertia quantity in a circuit. So to see that, we need to make this momentum, we need to derive something similar to this. So we have inertia term times our velocity. So for our circuit, we need to have flux linkage that's analog to momentum. It's equal to some unknown inertia term times current. So to do that, we already know that we already know this equation by Faraday's law of induction. So we can use the train of time derivative to derive. Yeah, just go with it. So this term here is the small signal definition for self-inductance. So L1 is defined as flux linkage over the current. Yep. And so we can further define our flux linkage as a time integral. Sorry. The flux linkage as an integral over current. Yep. So if we assume the current is the only source to this system, so the term C here should be equal to 0. Unlike the momentum of a particle, it is possible to have multiple sources that contribute to the buildup of the flux linkage of one circuit. So to see that, we can derive some equation like this. Yep. And this term here is known as the self-inductance. This one is known as the mutual inductance in our electrical circuit course. So yeah, it's basically like this. It's actually a two-state integral, and it's I think it's this integral can be worked out independent of the choice of the path. So yeah, it has integral path independency because there's no time in this equation, to simply put. Okay, finally, let's end this video by pointing out the analogy between the equations of physical quantities between electrical charge that's passing through some cross section and a point particle. So we call this a duality. It's only because they are sharing very similar law of motion. Where is it? It's here. So for a particle, its basic quantity is its location in space, and we can. So for an electrical circuit, we have electrical charge. So we have charge, particle. It's charge that's passing through a cross section. So if we take time derivative of this charge, it gives us the current, right? Yep. And the momentum is flux linkage. The kinetic energy is an analog to the magnetic energy. The Newton's law of motion is analog to the Faraday's law of induction. And we do have some, this is reactive power, and this is active power. Yep. So when there's all reactive power into the system, it's equivalent, into a circuit, it's equivalent to the circular motion of the particle. And yep, I think that's it. Thank you.